we'll continue continue the discussion on matter, which I forgot to record the first half or so. We were talking about density. This is lead brick. You know how much this thing weighs? You won't be able to see it. This thing weighs 26 pounds. Oh, 26 pounds. It's heavy. So you can pick it up, but just be careful not to smash your fingers. But that's lead brick. But lead brick, is that the most dense substance? Most dense? No. You know, as far as elements go, you know, the most dense is, I think, iridium, you know, osmium, around here. These are the most dense. Gold is highly dense. These guys are highly. These atoms weigh a lot, plus they can pack together tightly. So gold is 20. What is lead, though? Do you know? Does anybody know the density of lead? Well, we would look up, you know, in the old days, we'd look up the density of lead. You know, not that anybody would have it memorized, but you'd look it up in the CRC. You know, it'd be pretty easy to look up. But now, I mean, we can just look it up pretty quickly on Wikipedia. The density is 11.34, and so gold is about twice as dense as lead. You know, so you could take a look and feel that. Just to get a feeling, which is, you know, gold's about 20 times more dense than water. Lead's about 11 times more dense than water. Let's see. All right, now when we're looking at these types of things, you know, if we have a pure substance, that's fine. It's pure. But if we have a mixture, then a mixture is made up of two or more substances. And so how do we separate the substances from one another? The way we to separate the substances from one another is we take advantage of their properties. And so, for example, we could use something like distillation. Distillation takes a liquid mixture, here, and what it does is it tries to take advantage of different boiling points. So let's say you had alcohol in water. Alcohol boils at a lower temperature, water boils at a higher temperature. So you start heating it, and then the alcohol will boil off first. And then you cool it down. This is called a condenser tube. You cool it down, and that takes the pure alcohol that comes off because the water is not yet boiled. It takes the pure alcohol and condenses it back into alcohol and get it over here. This is one way. Alcohol is a little bit tricky to distill, though, because a little bit of water does get trapped over there. So the purest alcohol you can get is 95%, 180 proof. 190 proof. This distillation, we could try to separate it into pure substances. There are other techniques too. I mean, it depends on what type of mixture. This is filtration here. You know, so you could separate solids from liquids. This is gold. This is centrifuge for gold. You know, gold's much heavier. So you can sort things by, this is the old days, by density. Distillation, sifting, etc. This is another distillation apparatus. Filtering here. This funnel filters. Washing, remove the water-soluble stuff. Decanting is just pouring off the liquid. Maybe there's some solid stuff on the bottom of that. It's called decanting. Magnetism, you know, aluminum is non-magnetic, iron's magnetic, so you could easily separate aluminum from iron. Plastics are non-magnetic. Solubility just means, does it dissolve in water or not? So if you had a mixture of salt and iron, then you can just dissolve the salt away, leave behind the iron. So this is pretty much some of the techniques. There are more sophisticated techniques. There are more sophisticated techniques that take advantage of, I'll tell you. Take advantage of differences in solubility. And these techniques are called chromatography. And so, for example, if they're looking at inks, if you have a pen, usually that pen consists of a mixture of different colored inks. So you could separate the colors of ink depending on their solubility. Like it looks like the blue is more soluble, that is, it's carried. What you do is you put like alcohol in here. You put alcohol in here, what the alcohol rises up the paper. As the alcohol rises up the paper, it carries along different substances. And depending on the properties of the substances, we can separate it. So this dot here consists of 1, 2, 3, 4 different substances. You take a pair of scissors, you cut that out, and then you get the pair of substances. This is called chromatography. Chromatography has gone beyond that because now they use, rather than pieces of paper like this, they use columns of chromatography material. And this is very effective, so they just pour the liquid through here and then capture each of the components as they come out. This is called liquid chromatography. Liquid chromatography is very powerful and quite common. So this is liquid chromatography. And then we have gas chromatography, where things are carried by carrier gas and separated that way. So gas chromatography, you have these, actually this is really simplified, but you'd have, let's see if we have gas chromatography, a column, so you can see how long it goes on. So you have a gas, and you inject a sample in here, and then it travels a long distance. When you're traveling that long distance, the slower guys get left behind, the faster guys keep up. And it's like, if you're in a jogging race or something like that, everybody's bunched up at the start. But if the jogging race is long enough, then everybody's going to be separated, right? Depending on their pace. The same thing with the chemicals. The chemicals, this type of stuff is going to happen as well. And so these are techniques to separate out mixtures, and we can separate the mixtures into pure substances. The pure substances are going to be elements or compounds. However, we have to differentiate, because a mixture is going to have variable composition and a compound does not. So for example, here, some people might think of water as a mixture of hydrogen and oxygen. There are 2 hydrogens, 1 oxygen, but is it a mixture? Is water a mixture? No, water is not a mixture because the amount of hydrogen, the amount of oxygen is fixed, not variable. Whereas if I had hydrogen and oxygen gas, hydrogen and oxygen gas, then that is a mixture, because hydrogen and oxygen would be hydrogen H2 and oxygen O2, and so I could have any amount I want. Maybe I'll have 10% hydrogen, 90% oxygen, or vice versa, 90% hydrogen and 10% oxygen, etc. For this type of thing, some mixtures are very important, and they're characterized. For example, air. Dry air is important, so they measure the properties. What's the density of dry air? Et cetera, et cetera. How much does it weigh? This kind of thing. Other mixtures like, what is it? Have you ever heard of isotonic saline? Isotonic saline? isotonic saline gets put in these IV bags, and this mixture is very important because isotonic saline has a composition that is 0.9% sodium chloride. This is 0.90% WV. Do you know what WV stands for? Well, so far what I've been giving you is what's called the, well, I probably shouldn't get into it just yet, but W means weight, V means volume. So what this means is 0.90 grams of sodium chloride per 100 milliliters of saline solution. And so if you have 100 milliliters of saline solution, there's got to be 0.9. And that's a very important number because if this number is too high, then it would be hypertonic saline. If this number is too low, it would be hypotonic saline. So what's the problem with hyper and hypotonic solutions versus isotonic solutions? The problem is what's going to happen to your cells. You know, if you're having an IV isotonic, your cells are okay. But if you put in hypertonic, your cells are going to shrivel up. They're going to shrivel up like cucumbers, you know, shriveling up to make pickles. In other words, your cells are going to pickleize because all the water is going to be sucked out of your cells. Or if you put it in hypotonic, what's going to happen is that your cells are going to blow up like balloons, bigger and bigger. It could potentially pop, you know. And so it's very important that they use isotonic saline for this, otherwise your blood cells will pickle or blow up like balloons. And so there's certain mixtures that are very important. They're going to have a composition that's well characterized, right? But for the most part, we want to figure out, you know, mixtures are variable and this kind of stuff, so we want to figure it out here. Now, what if I did, you know, to separate the hydrogen and oxygen here is not so easy. Did I talk about separating nitrogen from oxygen? No? Like, it's not so easy because, like, let's take air, for example, because that's a more familiar mixture. Air consists of nitrogen and oxygen. Is there a way to separate out the nitrogen from the oxygen easily? And it turns out there are ways. There's a company called Liquid Air. Have you ever heard of Liquid Air? Liquid Air is a gas supplier. They sell all kinds of gases. You can buy helium, you can buy CO2, you can buy oxygen, you can buy nitrogen, or you can buy mixtures from them. Do you know where they get all the gases?
They synthesize it.
No, they don't synthesize it. How they get all the gases is they just get air and liquefy the air and then distill it. And so the air already has a lot of gases in it. And so they just pump the air, cool it down, compress it, get it into liquid form, and then start boiling off. So the helium and other things will boil off first. And then the less, you know, the things with lower boiling or higher boiling points will boil off later. So eventually the nitrogen comes off, and then the oxygen comes off, and they can capture that. But that's very expensive, right? To do. So the gases aren't cheap. But the feed material is cheap because they just get the air from outside, you know. And so it's quite a good business, I think. You know, it's like mining air is pretty easy. Now, it used to be in the old days, you know, people who with reduced lung capacity, they need a little bit extra oxygen. You know, maybe 20% oxygen is not enough. Maybe they need like 50% oxygen or something to give them a little boost. Otherwise, they, you know, the lung capacity isn't capable of supplying enough oxygen for their body, right? And so they'd wheel around a cylinder of oxygen. Well, where did that cylinder of oxygen came from? It came from a company like Liquid Air, or there are a whole bunch of others. You know, Linde, a bunch of these companies out there. They come from companies like that. But you know, these bottles of oxygen are cumbersome to wheel around. They're very heavy. They're in these steel bottles, and they're high pressure gases. And so, you know, I have a friend that worked at Liquid Air, and he was looking at the molecular sieves, you know. Molecular sieves are like, you know what a flower sieve is. Like, actually, we saw one of those up here on the separations thing. It's a flower sieve. Let me show you. Well, anyway, or filter, or whatever else. You know, sieve is just a filtration device. For flour sieves, you just get rid of the chunks of flour, you know, because. But if you make it smaller and smaller, the pore size, then we get filter paper like that. Filter paper, you can buy different size filter paper, you know, different size pores. You can buy very tiny ones, but very tiny ones it filters extremely slow. Or you can buy big ones which filters very fast but doesn't capture everything. So you decide which kind of filter paper to use. And they give numbers to those. Well, you know, this is going way beyond that. This is making the pores in the material so small that, what's bigger, nitrogen or oxygen? What's bigger? Nitrogen. These pores are so small that the oxygens pass through, blocking out the nitrogen. It's a little bit more complicated than that because they're very close in size. And they use other properties because oxygen is what we call magnetic, whereas nitrogen is non-magnetic, and so they could use some electricity or electric fields to help the separation. But essentially what they do is they get a little pump and then they push air through this filter. When they push air through this filter, the air that comes out is heavily enriched in oxygen. And so, as a company, I wish I thought of this idea when I was there at UCSB, but somebody else did, and they made a company that packages these sieves in a small container and then packages with a pump. So rather than carrying a cylinder of oxygen, they just carry around a little battery-operated pump that pumps air through the sieve, and then they can breathe enriched O2 air. Air is enriched in O2. So this would be a molecular sieve. Again, this would be what we call a physical separation. Now, physical separation is different than a chemical separation. So all these examples we talked about are physical separations. We usually use chemical equations to represent both physical separations and chemical separations. So a chemical equation would be something like this. This would be called the formula for water. Obviously, water can be in the solid state. If we heat up water, it'll go into the gaseous, or not yet. It'll go from solid to liquid to what? Gas. There's one more state of matter, and that is if we continue heating up water to higher and higher temperatures, what do you think is happening? As you heat up water to higher and higher temperatures, what do you think is going to happen? Well, what do you visualize when you heat up something to higher temperatures at the particulate level? High temperature means what? High kinetic energy. High kinetic energy means they're moving very fast. And so when you go to very high temperatures, these water molecules collide with such tremendous force, it knocks the hydrogen atoms off from the oxygen atoms. Not only that, it can break apart the atom a little bit, and that is, inside the atom are particles called electrons, and electrons get knocked off. And so if we continue heating this, what happens is at high temperatures there's no molecules that exist. They're only atoms. And a lot of those atoms have parts of them knocked off, the parts called electrons, causing it to be a charge. So for example, the sun is the classic example of a plasma. You aren't going to find any water molecules in the sun. In fact, you aren't going to find any molecules in the sun because the kinetic energy is way too high. It's going to easily break any kind of bonds holding the atoms together. Instead, you're going to find a plasma. And the definition of a plasma is what they call a partially ionized gas. That is, these collisions occur to form ions. Ions are just charged atoms. And so I'm not going to talk about plasmas at this time. We have thermal plasmas and we have non-thermal plasmas. Inside the fluorescent lamp is not like the sun. And the characteristics of the plasma inside the fluorescent lamp are totally different than plasma in the sun. You have the sun's plasma in that lamp, it vaporizes everything. And so this is called a non-equilibrium or non-thermal plasma. But there's all kinds of plasmas, so don't worry about that. Yeah. All right, so what we have here is these are all physical changes. This is melting, this is boiling, right? And we can go in the opposite direction. The opposite of boiling is called, and the opposite of melting is called freezing. And then we could go straight from solid to gas. Have you ever heard of solid to gas? Solid to gas is called sublimation, good. And the reverse, gas to solid, is called deposition. Deposition is hugely important in synthesizing high purity materials. You go straight from gas to solid, avoid the liquid state. And so in electronics, chemical vapor deposition is an enormously big topic. But anyway, this is physical. You know, physical separation would be, okay, we separate the sand from the water. I mean, this is just sand and water. Sand captured here, the water goes down here. But we can also use chemical equations to represent chemical changes. So this is a physical change here. If this were a chemical change, let's take methane. Do you know what methane consists of? Methane's molecular. It's a gas. Methane consists of one carbon and 4 hydrogens. It's going to be in this fixed ratio, so we say CH4. A molecule of methane consists of a CH4 unit. So let's take a look at this CH4 picture. This is kind of weird. There's a shape to it. This thing is just all loose. This is more the shape to it. This is what it looks like here. The space filling model. Carbon and the 4 hydrogens attached to it. Shown with links here. So we take methane, and when we combust it, it's no longer methane. So this is a gas. We combust it with oxygen in air. Oxygen in air is O2 gas. And then what happens is this is going to form CO2 gas, and it forms H2O liquid. And so when we combust it, it's going to form CO2, carbon dioxide. But we know that, conservation of mass, as we remember that from earlier, or conservation of matter. That is one other way of saying the conservation of mass or conservation of matter is by saying that atoms are neither created nor destroyed. Atoms are just rearranged in chemical equations. And so if we start off with one carbon atom here, we better end up with one carbon atom there. But now the carbon atoms associated with oxygens, CO2 has totally different properties than CH4. So there's nothing like before. This is a chemical change. The oxygen, the oxygen is going to end up both in carbon and with hydrogen. Right? And so that's where the atoms end up. But the total number of atoms has to stay the same. And so if we have 2 oxygens here, we've got to end up with 2, but we ended up with 3. That means we got an extra oxygen. That can't be. It can't be. And so what we have to do is we have to always balance chemical equations. To balance chemical equations, like here, 4 hydrogens, we only end up with 2 hydrogens. And so to balance it, that means we can't just produce 1 water. We have to produce 2 waters. Because I can't change this. If I had 4 hydrogens here, I got an easy fix. I'll just make a water with 4 hydrogens. Can I make a water with 4 hydrogens? No, because that's no longer water. And so the only thing I can do is I can just say that there are 2 waters formed, 2 molecules of water formed. And that takes care of all the atoms. And over here I have 2 oxygens, but I got 4 oxygens. Now I'll just have to say there are 2 O2s. I'd never say that there's no 4. O4, who knows what that is? Well, I know O3 is ozone, but O4 doesn't make any sense. So we changed this. We never changed the subscripts here. We only changed what are called the coefficients. The coefficients can change, but do not change the subscript, because if you change the subscript, that's going to change the ratio, which changes the composition, which means it's no longer the same compound, no longer the same substance. or element in this case. Because this is, what is this? Is this compound or element? Compound. This would be element, compound. These are all molecular compounds, methane, CO2, and water. How do you know? Well, that requires a little bit of memorization, because a lot of people will think, carbon dioxide is molecular, so silicon dioxide should be molecular too, but silicon dioxide is not molecular. Silicon dioxide is quartz. Quartz is not molecular. So it requires a little bit of memorization or a little bit of familiarity to deal with that. And so these are what we call chemical, and these are balanced chemical equation. Balanced chemical equation says that the total mass here has got to equal the total mass here. Which it pretty much does, except for one thing. That one thing is, what else is produced in this reaction? When we combust methane, usually you combust methane for what? What do you do with the natural gas? You combust it to generate heat to warm up your pot of water. And so what else we produce here is energy. Now energy is a little bit tricky, because have you heard of this equation, E equals mc squared? E equals mc squared? Or delta E is equal to delta mc squared. Do you know what delta means? Change. And so the change in energy is equal to the change in mass times, does anybody know what C is? Yeah. And so E is energy, M is mass, and C is the speed of light, which is a constant in a vacuum. And so that means any energy change is associated with a small mass change. That mass change is so small, nobody ever noticed it. And still nobody ever notices mass change. The mass change is so minuscule, you can't measure it with our balances. The only way that people found out that there was a mass change was when they did nuclear reactions. Like, for example, a nuclear explosion. In a nuclear explosion, or nuclear reaction, or nuclear process, the energy changes are so massive that the mass change is measurable. Otherwise, you can't measure the mass change. And so, remember, the conservation of mass is back in the 1700s. Nobody ever noticed it. The mass before, the mass after are the same. And still, nobody can notice it. In chemistry, we don't. In chemistry, we just say the mass is the same. But if you're a nuclear chemist, you can't do that. If you're a nuclear chemist, you have to do this. You have to combine it. And so you have to say the conservation of mass and energy, which we'll talk about a little more later. But the conservation of mass and energy. The total mass and energy before has to equal the total mass and energy at the end, and then we're good. But what impact does it have for you? None. What do you need to know? Well, you need to know the mass doesn't really change for chemical reactions, even though there's energy generated. Now, there could be energy generated. When energy is generated, we call it exothermic. Exothermic. And the energy, the energy comes in different forms. It could be electrical energy, it could be all different kinds of energy. But there are other things that require energy. So for example, this. How can I separate the hydrogen from the oxygen in water? Can I filter it? Is it possible to filter out the hydrogen from the oxygen in water? Well, even if, what if I use one of those tiny, tiny sieves, the molecular sieves? Can I filter out the oxygen from the water and the hydrogen from the water? No. Can I distill it? If I distill water, can I separate the hydrogen from the oxygen that way? No. So compounds, these cannot be separated by physical means. There's no physical technique that can separate the hydrogen from the oxygen from the water. If you wanted to do it, most of the time we don't want to do it, but nowadays we want to do it because compounds can be separated only by chemical means. Okay, one of the chemical means I'm going to use is I'm going to put energy in here. And this energy is going to be electricity, which we call electrolysis. And so I'll put this energy in here and I'll get hydrogen and oxygen. So these are gases, as we know. Is this balanced? Do I have the right number of atoms on the left and the right? No, this is not balanced. Tell me how I'm going to balance this. Which should I change?
Coefficient of 1.
Coefficient of 1 where?
No, in water.
On water?
It's 2H2O.
Oh, 2H2O, okay, change that to 2H2O and 2 in front of the hydrogen. And then we're good. That's what we call a balanced chemical equation. And so it's pretty much, you can only use chemical means. Electrolysis is one of the most common chemical means to separate the components of a compound. You can electrolyze water without too much difficulty here. Let's hope this is working. Down here, there are 2 platinum wires here. Let's stick platinum wire in here. Gases are compressible, here, and so this is compressed here, but I'm going to bleed. For some reason it's not. It's not letting me. Okay. Now, do you see? This is just what we call a U-tube. On one side, I'll put the positive charge. On the other side, I'll put the negative charge. Just push all the negative to one side, the positive to another. I'm going to create a voltage. Well, I can create a voltage easily because we have a power supply here. Let's create the voltage here in the power supply. Make sure it's off. It's off. Plug my computer. So I have the what we call the positive lead on the power supply. Which side do I want to make positive? Maybe this side. Doesn't really matter, just pick one side. And the other I'll make negative, like this. Just turn on the voltage here. Low range, minimum. Right now I'm at, I don't know, 0.23 volts. Crank this up. Actually, the low range is kind of low. I'm going to go higher. This is in millivolts. So 166 oh, is that volts? It can't be 165 volts. It would be way too high. It's got to be millivolts. I think I'm at 2 volts here. This gets at about 3 volts. I think this power supply is good too. Oh, is it broken? Oh shoot. That's broken. platinum came off. Platinum is very expensive, so the platinum was soldered onto a piece of copper. And I didn't look at it carefully before. We'll just have to do the alternative here. This is called electrolysis of water. You could do it with like a 9-volt battery. A lot of people are interested in electrolysis of water. They're interested in electrolysis of water because of hydrogen. Hydrogen is a great fuel. This looks like a homemade electrolysis kit, so. Let's speed it up here. See what kind of batteries he uses. He's using stainless steel. Stainless steel is okay. Stainless steel is resistant to corrosion. Platinum's better. Platinum is much more resistant to corrosion, so eventually his stainless steel will start to corrode. And then he's going to charge one of the stainless steels, one positive and the other. These bottles he's using as collection. And so this basically this. The gases are less dense than water and they'll rise. So you can collect the gases in these inverted kind of bottle things. And then he's going to capture the gases in there by water displacement. So he's probably going to fill all this with water. So let's take a look. This is just a way to capture it. And so he's taking normal tap water. He's putting some other chemical in here. If you put some other chemicals, it could speed it up and make it easier. So he's putting something called sodium hydroxide. I usually put a little bit of sulfuric acid in there to speed it up. But you know, technically you don't need to have that in there. But it's okay. He did that just to speed things up. Now, if you look at this thing, it's just, these are just plastic bottles with the holes cut in the bottom so that the gas, okay, basically the gases are going to rise up in here. And, one gas will be hydrogen, the other gas will be oxygen. Will rise up and capture them, separate them as pure substances here. And so we'll continue on. So he puts that in there. And so he has the little capture bottles. You see the little capture bottles that he has there to capture the gases. He's using a 12-volt DC power supply. And he's measuring the current, that is how much what we call charge is passing through the line. There. It looks like he's not going to fill those water bottles. He's just going to capture the hydrogen as is. And so what's going to happen is there's going to be a whole bunch of air. I didn't want any air contaminating my hydrogen. Since I didn't want any air contaminating my hydrogen, I filled this tube up with water. So there's no air in there. And so his gases are going to be contaminated with air based on this setup here. And so, let's see. Okay, he's trying to purge the air out, you know, by generating enough gas, but still. So he waited 3 minutes to purge the air out, but still there's going to be a little air contamination in there. Okay, now when you look at this, you can see the bubbles forming. And so there's bubbles of one. Look at the bubble rate. That bubble rate is a lot slower than the other. This bubble rate is a lot faster. That way I know which one's being produced. Which one's being produced on the right? Hydrogen or oxygen? Which one's going to be produced faster? Hydrogen or oxygen? Hydrogen or oxygen is going to be produced faster. Hydrogen. We need twice as much hydrogen as oxygen. And so the hydrogen is going to be produced 2 times faster. You can also see this in the volume of the containers here. Let's take a look. Yeah, do you see that? Lots. I don't know if he has that right, because that looks a lot slower. That looks like the hydrogen. Well, whichever. So he's collecting in balloons. This is like a homemade apparatus here. Oh, now it's easy to tell. Which one's left? This got to be hydrogen. So he disconnected the power supply and then he filled the plastic bag with hydrogen. Hydrogen is less dense than air. Oxygen is actually more dense than air. So oxygen weighs a little bit more than nitrogen. And the air is a mixture of oxygen and nitrogen. All right, so that's one way you could do it. Electrolysis. You probably can get away with a 9-volt battery. You know, you could do this. You probably can find it on YouTube. But what are we on time? We're out of time, so we'll stop here. Tomorrow we're meeting in lab. You know, normally on lab days, make sure you wear proper footwear. You know, lab, there's broken glass on the floor and other stuff, chemicals. So you don't want sandals. The weather's kind of, you know, when the weather warms up, people like to wear sandals, but it's not good to wear sandals in the lab.
Do we need our goggles tomorrow?
Tomorrow you don't need your goggles, but if you have goggles, bring them.
Do we have a facility with stuff? Or?
Yeah, you have a locker. Oh, wait, is there people still trying to add? If you're trying to add, can you make it to the afternoon class? There's space actually available in the afternoon. Is anybody 2:30 to 4:30 and 2:30 to 5:10 Thursday? I forgot to check roll today, so.
Another question for the homework. I've just been answering as many questions as possible just to practice. Is that what you ideally want us to do? On Newton?
Yes. Yeah.
So
eventually it'll stop asking you questions.
Oh, really?
Yeah.
Okay.
Then you're 100% done.
Because it usually says you mastered the course after like 4 or 5, but then I just continued to practice.
Okay, yeah, then that's fine. If you've already mastered it, you can either stop or continue to practice. It's good to continue to practice.
Right, that's what you want us to do. Okay, thank you.
Or get ahead, you know, start working on the other stuff.
Able to fill out the wait list.
You know, I forgot to take a roll today, so I got to do it tomorrow.
Okay, that's fine.
Are you're number 1 on the wait list?
2.
Number 2? Who's number 1? Did I already add number 1?
Yes.
Okay, so number 2's okay because nobody came to me and said they missed yesterday. So you're probably okay then. Number 3, I don't know.
So it would be today at 2:30?
Yeah, today at 2:30. There's space. Are you interested in that class?
I'm not sure if I can, but I'll.
Okay.